Okay, the purpose of this video is to go over the derivation of the kinematics equations a little more slowly than we had time to do in class the other day. All right, so really, while we think of there as being 3 kinematic equations, there are really only 2, and then the third one is a combination of 2 of them. So what are those equations? So we're going to start by reminding ourselves that the acceleration is the derivative with respect to time of the velocity. And for the kinematic equations, we're going to have constant acceleration. So this acceleration A is just a constant. V, however, is a function of time, and X is a function of time. Okay, so we want to keep that in mind as we write. Okay, and so we would like to solve this equation, right, to get something, an equation that's in terms of V instead of solving for A. And so to do that, we need to integrate. And we're going to make that an iterated integral, meaning an integral that has an endpoint. And we're going to consider integrating from some time that we'll call t0. So this is whatever time we start measuring, okay? And then note that at t0, we're going to assume that v of t0 equals v0 and x of t0 equals x0, okay? And so we want to start our object moving at some time t0, and then we're going to integrate until time t. So our other, so we're integrate from some time t0 here to time t, okay? And that means that we're going to want our equation in the end to be in charge of t, in terms of t. And so if we just integrate our original equation, a equals dv dt, and we want to get something in terms of t, that's going to make things kind of confusing. And so we're going to introduce what we're going to call a dummy variable. And we're going to name our dummy variable t prime. So that's to remind us that it's like a time, but it's not the same time as this t that we're using to get our final equation in terms of, okay? So now we're going to write a as dv of t prime dt prime. It's still that same constant. We're just writing it in this different way. And so then we are going to integrate from some time naught to some later time t over dt prime, okay? And we're going to remember that this is dv of t prime dt prime dt prime, okay? And so by the fundamental theorem of calculus, this thing on the right gives us v of t prime evaluated from t prime equals t0 to t prime equals t, which is v of t minus v of t naught. Okay, so that's the right side of this equation. Now we're going to go look at the left side of the equation. Now remember that this a is just a constant. So this is an integral that you should be able to do. If you need help or need to review your integrals, feel free to come see me at office hours. But for right now, let's do this integration. And so that integral of this constant a from t0 to t is going to be a times t prime evaluated from t prime equals t0 to t prime equals t. So that's a t minus t0. And that equals, oops, v minus v naught. And then we're just going to rearrange, so v equals v naught plus a t minus t naught. So now we've got our first kinematic equation. Let's highlight this in a different color. We'll make these purple. All right, so we've got our first kinematic equation. Call this equation 1. All right. Now we want to get a second equation, a second, hopefully independent equation. So to do that, we need to use a new piece of information. So our new piece of information that we haven't used yet is that v is dx dt. And we're going to do basically the same thing that we did before, okay? Except, and we're going to again write v as a function of t prime instead of t. So that means we're doing dx dt prime. And we just found above that that's equal to v naught plus a. Now we're replacing all our t's by t prime. That's our dummy variable. Minus t naught. Okay. And we are going to do the same thing that we did before. Okay. So we are going to integrate dx dt prime from t naught to t. Okay. And this is going to give us, we do this two ways. First, by the fundamental theorem of calculus. And so then we get x of t prime evaluated from t naught to t, which is just x of t minus x of t naught. Okay. And then on the other side of our equation, we're going to plug in this thing here. So we're going to also say that because dx dt is equal to v, then we can say that this is also equal to t naught, integral from t naught to t, v naught plus a t prime minus t naught dt prime. Okay. Now I'm going to rearrange this a little bit to just put all my constants together and all my t's together. So notice this t naught is a constant, a is a constant, v naught is a constant, t prime is the thing I'm integrating over. Right? So let's just rearrange that a little bit. Got the integral from t naught to t, v naught minus a t naught plus a t prime t prime. So this thing is just integrating a constant. So we've got v naught minus a t naught t prime evaluated from t prime equals t naught to t prime equals t. And then now we've got this thing here is just linear. And so the integral of t prime is 1/2 t squared. We've got our constant a out front, so t prime squared over 2, evaluated from t prime equals t naught to t prime equals t. Okay, so let's plug those in. So we've got v naught minus a t naught times t minus t naught plus a t squared over 2 minus a t naught squared over 2. Now we're going to rearrange some things. So we're going to pull out all our a terms together and all of our v terms together. So we've got v naught times t minus t naught. That's all our v terms. And then all of our a terms, which is t squared over 2 plus, minus t naught plus t naught squared minus t naught squared over 2. Sorry that I did those in kind of a weird order. I'm going to highlight which one goes with which. So this one is this term. This one is this term. This one is this term. And this one is this term. Okay. So notice that all of this thing is t minus t naught squared And we've also got v naught t minus t naught. Okay. So this is one side of our equation. The other side of our equation was up here, this x minus x naught. Okay. So let's put these two together, and we have our second kinematic equation, x minus x naught equals v naught t minus t naught plus a t minus t naught squared. Oh, this should have been a 1/2 too. There. Okay. All right. And then we're going to rearrange to write this in terms of x. So x of t is x naught plus v naught t minus t naught plus a over 2 t minus t naught squared. Okay. So really, these are our two kinematic equations. Now, this one here, and then our second one up here. I'm going to copy it down below. Put them together. Oops. Well, whatever. Pasted it, isn't it? That's an image, but that's okay. All right. I got equation 2. Now, it will be very common that you have some combination of your v's and your x's, but you don't know anything about t. And so it's useful to have a version of these equations that don't have t in them, okay? And so in order to generate that, we're going to solve equation 1 for t minus t naught, right? So to do that, I'm going to subtract v naught from both sides and divide by a. So that's v minus v naught over a. It's going to equal t minus t naught. Again, that came from this equation here, equation 1. And now I'm going to substitute this into equation 2. So that gives me x equals x naught plus v naught, v minus v naught over a, plus a over 2, v minus v naught over a squared. Okay. Now, I can combine some terms here. So how are we going to do that? I'm going to move my x naught over to the other side, not for necessarily any particular reason other than that's the way it's often written. I'm going to pull out a factor of 1 over a because there's a 1 over a on all of the terms on the right that are left. And then I've got v naught v. Let's highlight where that came from. V naught v minus v naught squared. From here. Plus, I need to square that v squared minus v naught. So, and I've got a factor of 1/2 on all these. So, plus 1/2 times v squared minus 2v v naught plus v naught squared. And then notice there was an a squared on the bottom and an a on top, so I just pulled that 1 over a out over here. Okay. Now let's combine all these to make things a little bit simpler. So I've got x minus x naught times 1 over a is v squared over 2 minus v naught plus v naught squared over 2. No, sorry, I screwed that up. No. Scratch all that. It's like, this is not giving me the right answer. What did I do? Sorry, scratch all that. Everything inside the parentheses again. No, that was right. Oh well. Okay. I'm going to fill out a factor of 2. And then let's do this in a different order. Okay, so this is v squared. And then I've got, I've pulled out my factor of 1/2 this time. So I've got v naught v minus v naught v. So those cancel it out because this factor of 2 cancels out here. And then lastly, I have v naught squared here. that's negative, plus a half v naught squared, so that's going to be minus v naught squared over 2, but I've pulled out my factor of v naught squared, so it looks like this. Okay. All right. Sorry, I got a little bit messy on that algebra, but if you check it, you should find the same thing. So we often write this as x minus x naught equals v squared minus v naught squared over 2a. We can think of this as equation 3, but again, this is not really a new equation. This is a combination of our first two. Okay, so those are our 3 kinematic equations. One other quick note, I want to just remind you that x is a function of time. Oh, not y. V is a function of time, and then we've got a bunch of constants in these equations. We've got our acceleration, which is constant, our v naught, which we may or may not know, but which is a constant. It's whatever velocity it started with. Our t naught, again, which we may or may not know, but it's whatever time it started with. Our x naught, which is our initial position. Again, we may or may not know it's whatever time it started. It's whatever position it started at. Okay, and then t also is a variable that can change. So on the left here are the variables, and then on the right are the constants. Okie doke. Hope that helps.